Respected guests, ladies and gentlemen, distinguished President Jin Chibiao, dear meeting friends, hello everyone. So we now officially kick off the successful construction of the JUNO and the release of the conference. So this event is co-organized by 70 domestic and international research partners. We have jointly completed the experiment construction. And on behalf of all of the researchers and the Institute of High Energy Physics of the JUNO International Collaboration, I warmly welcome all of you and express my sincere gratitude for your presence. Now I would like to introduce the leaders present today. Vice President of the Chinese Academy of Science, Mr. Ding Chibiao. Secretary of the Jiangmen Municipal Party Committee, Mr. Chen Anming. So we have a lot of guests joining us, and please give them a round of applause after I introduce all of them. Ambassador of the Czech Republic to China, Mr. Martin Toko. Ambassador of the Slovak Republic to China, Mr. Milan Lajek, and Minister Cristina Carranza from the Deputy Head of the Italian Embassy. Now we also have guests from Germany, Thailand, Holland, Hungary, Spain, Norway, Holland, and also consul representatives from the U.S., Brazil, and Thailand consulate in China and Italian embassy in Shanghai. And we have a lot of representatives joining us. Fermin Kuvas joining us from the director of the Beijing office of the Beijing National Center of the Scientific Research, He Hong, director of the Beijing office of the German Helmholtz Association, Oliviello, vice chair of the Italian National Institute for Nuclear Physics, Evgeny Yavushev, head of the Boking High Energy Physics Laboratory at the Joint Institute for Nuclear Research, Russia, and director of the Institute for Nuclear Research of the Russian Academy of Sciences, Maxim Labanot, and Maraka, director of the Research Facility Department, Ministry of Education and Youth Sports, Czech Republic. And we also have leaders from Guangdong Province, Wu Shiwen, Deputy Director of the Guangdong Province Department of Science and Technology, and Chao Yang, Vice Mayor of Jiangmen City. And also we have representatives from the different parts of the Guangdong Province, Jiangmen City, Kaiping City, and Jinji Town, and also high-level supervising leaders present today include Chen Liang, Deputy Director of the Major Science and Technology Task Bureau, Chinese Academy of Sciences, and Li Yuhui, Deputy Director of the Bureau of the Frontier Sciences and Education. We also have representatives from the International Cooperation Bureau and Computer Networks and so on. And the successful completion of the projects is also attributed to other supporting organizations. We have Liu Dan from the Taizheng Nuclear Power Joint Venture, Chairman and General Manager, joining us, and Liu Fuming from the Yarrow River Survey Planning and Design Research Institute, and Che Diecheng from East China Engineering Consulting Company Limited, and from Power Construction Corporation of China Kunming Survey and Design Research Institute, Liu Yuanyuan, and also Pei Liming from the China Hydropower 6 Engineering Bureau, and also General Manager Sun Chengming from the Henan Jianyuan Construction Company Limited, and from Northern Night Vision Technology Nanjing Research Institute, General Manager Chang Yunming, Fang Jiankun from the Zhejiang Tangcheng New Materials Technology Company, and General Manager Li Guoxing from Zhejiang Southeast Space Offering Group, and Jiang Lai, Deputy General Manager from Shenzhen Dadi Curtain Wall Technology, and Chen Peng from the Sinopec Jinling Petroleum Company Limited. We have received continuous support from the experts. We would like to thank Academia Zhang Huanqiao and Zhe Hesheng. And also present today also includes Wang Shen, Party Secretary of the Institute of High Energy Physics and the Deputy Director of the Wei, members of JUNO International Collaboration Team, and meeting friends. Let's give a warm round of applause to welcome the leaders and guests. The Chinese Academy of Sciences supported the approval and construction of the Jiangmen neutrino experiment in 2013 as a strategic priority research program. Now I would like to welcome the first speaker, Vice President Ding Chibiao from the Chinese Academy of Sciences to deliver a talk. Let's welcome Mr. Ding. Distinguished dear experts and guests, meeting friends, good morning to all of you. Today, we are gathered here. We have a lot of friends joining us. We have friends from China. We have domestic physicists, scientists, and experts. We also have colleagues from more than 10 countries. And friends are gathered here to attend the completion ceremony of the JUNO press conference. And also this is also a release conference for the first physics result. On behalf of Chinese Academy of Sciences, I would like to extend my congratulations to the completion of this project, of this program. I would also like to extend my warmest welcome to all of the experts. I would like to extend my warmest welcome to all of you. I would also like to thank people who provided continuous support to this program, NDRC and the Ministry of Finance and Guangdong Province and Jiangmen government organizations for your continuous support. My heartfelt thanks go to all of you. The Chinese Academy is an important research organization for natural researchers and researchers in other fundamental sciences. We have made some tremendous, remarkable achievement. For example, the ring and other theories, physics as well. Meanwhile, until 1988, we built the first scientific large physicists, and we have been running 24 scientific devices. So the number of the scientific devices accounts for half of the country's total. Nutritional physics as an interdisciplinary field, bridging particle physics and astrophysics and cosmology, and is a hot area of particle physics research, and is also known as the study of ghost particles. Capturing them precisely requires the deep integration of large scientific facilities and the frontier of the physicist. The Daya Bay nutritional experiments discovered the third neutrino missing angle in 2012. This project was praised as an opening the door to the future development of the neutrino physics, marking another scientifically significant and influential achievement by our country in cutting-edge international research. To further expand the nutritional research results and promote the major discovery in basic sciences, the Chinese Academy of Sciences carried out top-level planning and forward-looking arrangement in 2013, launching the Jiangmen neutrino experiment, A-class strategic pilot science and technology program, and the Guangdong provincial government likewise initiated special support for the Jiangmen neutrino experiment the same year. So JUNO is also a major international collaboration project in fundamental sciences that brings together the world's expertise. The collaboration includes 74 research institutes from 17 countries and regions and about 700 researchers. This fully demonstrates our nation's open, cooperative, and moving approach to international cooperation, and it is a concrete example of our academic leading innovative development in science and technology and shouldering the responsibility of major country. With strong support from all sides and the close cooperation of Chinese international scientists, the Jiangmen underground nutritional experiment was successfully completed and began taking data in August this year. As the world's first completed next-generation ultra-large scale, ultra-high precision nutritional experiment, it updated the world's records for the precision of two oscillation parameters measurement based based on the only 2 months running data. I hope that this project team will continue to work hard, ensure the efficient and smooth cooperation of the Jiangmen neutrino experiment, improve our operational performance, and collaborate closely with the scientists worldwide. Finally, on behalf of the Chinese Academy of Sciences, I would like to thank all of the international collaborators, the various ministries and commissions, and the governments at all levels of the Guangdong Province and Jiangmen City for their strong support of our work. I wish everyone success in the work and good health. Thank you. Thank you, President Ding, for your speech. The success of the Jiangmen neutrino experiment construction would not have been possible without the strong support of effective guarantees from Guangdong Province and the city. The Guangdong Provincial government approved and supported the construction of the Jiangmen neutrino experiment, and the Jiangmen municipal government provided comprehensive support. Now I would like to invite Mr. Chen Anming, Secretary of the Jiangmen Municipal Committee, to deliver a speech. Respected Vice President Ding Chibiao and Academician Zhang Huanqiao, Academician Chen Hesheng, Academician Wang Yifang, and Director Zhao Jun, and Secretary Wang Sheng, and Deputy Director Wu Shiwen, and dear experts and friends, good morning to all of you. On this morning, we are tremendously excited and proud to witness the completion and commissioning of the world's first generation large-scale neutrino experiment facility and the release of the first physics results. This is a major milestone in our country's basic scientific research and a landmark achievement in building Guangdong, Hong Kong, Macau, Greater Bay Area into an international center for science and technology innovation. Here, on behalf of the city of Jiangmen, I extend my warmest congratulations. I express heartfelt thanks to the leaders at all levels and people from all walks of life who have cared for and supported the construction of the facility of Jiangmen. I also pay my highest respect to the researchers and the construction workers who have pursued innovation and worked tirelessly. I warmly welcome the officials, embassy and consulate representatives, and scientists who have come from afar. Since the 18th National Congress of the Communist Party, the party's Central Committee with Xi Jinping at its core has consistently planned and promoted scientific and technological innovation with global perspective, proactively initiating international science and technology cooperation initiatives, taking the lead in organizing large international scientific programs and projects, and supporting the researchers from various countries to work together so that science and technology can better benefit humanity. The Jiangmen Neutrino Laboratory is a major international scientific cooperation project led by our country. So we are very grateful for being able to work with this program. And this program involved 17 countries and regions and 75 research institutions and universities. And this is actually a practice of deeply implementing the concept of community with a shared future for mankind and promoting open scientific technology cooperation. Jiangmen, it is an important city for China's opening up as well. So we have been implementing the spirit of the 4th plenary session of the 20th CPC Central Committee and the important speeches and instructions given by the General Secretary during his inspection of Guangdong. We advance education, science, and talent development in an integrated manner, fully leverage innovation leading role of the national large scientific facilities, and better serve the construction of a technically a strong nation. First, we will continue to deepen cooperation with the Chinese Academy of Sciences and international collaborative research institutions. And we are also a famous tourist city as well. We are going to gather more high-end talent and support universities and enterprises form innovation consortium, jointly participate in scientific research program, and cooperation and promote cutting-edge scientific research results toward industrial application, achieving a deep integration of the technological innovation and industrial innovation. Second, we will accelerate the construction of an international youth science education and research base, leverage the roles of the Chinese academies Sciences and the Jiangmen Science Popularization Media Group to jointly build an immersive science museum and integrate frontier science and technology, develop high-quality courses and high-quality programs, and attract more study tour young people from Hong Kong and Macau and domestic and overseas regions. Third, we will wholeheartedly provide comprehensive high-quality services, carefully ensure all necessary elements, create a friendly and comfortable environment for scientists from all countries, fully support the high-level cooperation of the laboratory, and contribute Jiangmen's efforts to producing more fundamental and original scientific achievements. We firmly believe that under the strong leadership of the Party Central Committee, under the effective guidance of the relevant national ministries and commissions, the Chinese Academy of Sciences and the Guangdong Provincial Party Committee and provincial government, and under the joint efforts of all scientific researchers, the eye of the universe, hidden 700 meters underground, will surely unveil more mysteries of the matter and the cosmos and contribute Chinese wisdom to the progress of the civilization. Finally, congratulations on the successful construction of the facility and the release of the first business result. I wish everyone good health, happiness, and all the best to all of you. Thank you. Thank you, Mr. Ming. After 10 years of participation and construction, the Jiangmen.
Now, let's give the floor to Academician Wang Yifang, spokesperson and project manager of the JUNO collaboration.
Good morning, everyone. Thank you very much for coming. Let me give you an introduction of the JUNO experiment. So the purpose of the experiment is neutrinos. Neutrinos are fundamental particles of our matter world and very important in cosmology, particle physics, and astrophysics. In our standard model of particle physics, the mass of neutrinos has to be 0. But in the standard model of cosmology, the mass has to be non-zero. So there's a fundamental kind of contradiction. So we had to figure out which one is right. And the evolution of the universe also very much depends on the mass of neutrinos. There's a way to detect the mass of neutrinos, which is the neutrino oscillation. So indeed, 20 years ago, we realized that there is a neutrino oscillation, and neutrino does have a mass. So we had to modify the standard model of particle physics. In the past 20 years, we managed to measure 3.5 fundamental mixing parameters of the neutrino oscillation, which is sine squared 2 theta 1, 2, sine squared 2 theta 2, 3, datum squared 2, 1, and the absolute mass, absolute difference of the datum 3, 2. There's another mixing parameters called the sine squared theta 1, 3, which was measured some 250 kilometers away from here in the diabetic experiment. And now, in this experiment, we like to measure the sign of the datum squared 3, 2, and also the CP phase, delta CP. Indeed, in the far future, we are going to upgrade the JUNO experiment to be a neutrinoless double beta decay experiment. So in Diabei, in 2012, we actually observed a new type of neutrino oscillation and denoted as theta 1, 3. And you can see the value has been measured here. And this table shows you the best value up to now with a precision of about 2.8. So the next step after the diabase experiment is actually the Jiangmen react neutrino experiment. Originally, we called it diabase 2, and we looked around in this region of the Guangdong, and the first candidate site was here. But you see there are many reactors here around. They are not actually in an ideal kind of arrangement. So finally, we realized that Taishan and Yangjiang is the best place for this kind of experiment for the neutrino mass hierarchy, and we couldn't find a very good place here for the JUNO experiment. And you realize that we need to have a distance to the reactor of about 53 kilometers, and with the variation of the distance difference by less than 200 meters. So it is not very easy to find a site, and this location where we are here is really the best in the world. And by building this experiment at this exact location with equal distance to the Taishan and Yangjiang, we can determine the neutrino mass ordering and also have a precise measurement of the oscillation parameters and also study supernova neutrinos and etc. The fact that we are able to measure the neutrino mass hierarchy using react neutrinos is demonstrated here in this plot. Indeed, in 2008, right before we had our result of diabase, we discussed the future of the neutrino experiment in China, and we realized that the mass hierarchy is actually a good topic for this kind of a study. And indeed, if you see the energy spectrum of neutrinos from reactors, minor small distortions actually tell us the information of the mass ordering. So these little wiggles actually require us to have an energy resolution of 3% to measure the energy resolution from reactors. So that's actually the key to realize such an experiment for this scientific purpose. So in 2009, we determined the concept and the key parameters of this experiment, which is the size of the detector, 20 kilotons, and the energy resolution 3%, exactly for this reason. And also, we have two reactors next to each other, so we have 36 gigawatt thermal power, the largest ever you could ever imagine to be able to find in the world. And baseline two reactor, 58 or 53 kilometers. Starting from 2009, we started the key technology R&D. First one is the new type of photomultipliers, so that we could increase the detection efficiency by factor 2, and that's actually the key to achieve this 3% energy resolution. And the secondly is very transparent liquid scintillator, which can give you transparency, let's say, factor 2 better than what we have achieved in the past. So these two key R&D actually is a guarantee for the success of the experiment. And indeed, the two companies which actually help us to study and to realize this kind of new materials, new equipment are actually here. So we thank them very much to collaborate with us to achieve this very important technological advancement. So the detector itself is about 40 meters diameter, and in the middle is 20 kilotons of liquid scintillator. Comparing to past experiment, you can see here, we are factor of 20 larger than Camland, and almost factor of 40 larger than Bolzano in Italy. And on top of it, we need to have a lot more number of photons to be able to achieve the needed energy resolution. So technologically, this is a very difficult and a very complicated experiment. So we had to build the largest ever underground cavern with a span of diameter of 59.5 meters, the largest in China and probably in the world. and also the world's largest aquatic tank, which is factor of 3 larger than snow in Canada, the most transparent liquid scintillator, almost factor 2 larger than what we have achieved in Daya Bay, and also factor 2 larger detection efficiency over what people have achieved in the past in Super K and CamLab. The goal is not only react neutrinos for mass ordering, for precision measurement of mixing parameters, but also for solar neutrinos, for supernova neutrinos, for atmospheric neutrinos, geoneutrinos, and also search for proton decays, and also the stereo neutrinos, etc., for new physics. The project was proposed, as I said, in the year of 2008, approved by Chinese Academy of Sciences in the year of 2013, and subsequently in many other countries in the world in the year of 2014. The civil construction started in 2015, and the detector installation started in 2021. And we finished the construction in the year of 2024 and start the water feeding and the liquid scintillator feeding. By August this year, we finished all the feeding and we started the data taking. The underground laboratory is just next to it. You see this is the entrance tunnel, which is this one, which is roughly 1,265 meters long with a slope of 40%. And then there's another vertical shaft with a total height of 564 meters. The underground laboratory is arranged in this way, somehow complicated, but there's a need for engineering point of view and for safety point of view, and also for the physics point of view. And this is the surface building we are actually situated here. The detector installation is a very complicated process. You are going to see a video a moment later. And indeed, we came up with a very innovative installation process, which means that we start from bottom up, a steel structure, and then from top to the bottom, a critical tank. In the meantime, we also install our phototubes from top to the bottom, and finally, we cover the whole detector with with a veto detector for cosmic rays. So the whole installation process is actually completed in about 4 years successfully and also safely without any incident. So by the day of August 22, we had finished the feeding of the liquid scintillator, and also by 26, after 3 days of calibration of the detector, we started the physics data taking. So we can see the total volume of the liquid scintillator and also the high purity water. So in summary, this is an effort by more than 700 people for more than 10 years, and also more than 1,000 people from contractors and more than 30 contractors. And indeed, finally, you are going to see later on, the performance of the detector is up to our specification, and we happily announced today the physics results. So finally, I would like to thank all the funding agencies in China and also in the world, the Guangdong, Jiangmen, and Kaiping local governments, and all the contractors, people, their team, and all the foreign embassies, consulates in China. Thank you very much.
Okay, thanks. To give you a better understanding of the construction journey for JUNO, we have prepared a short video for you. Take a look.
这么大一个实验，最后要完成你设定的一个竞争目标时，我们每一步都必须走对了，每一步都必须正确。
中微子，揭开宇宙奥秘的金钥匙。测量中微子质量顺序是国际中微子研究的前沿热点目标。对它的研究将敲开新物理的大门。江门中微子实验位于广东省江门开平市金鸡镇打石山下700米深处，距离台山和阳江核电站各53公里，是测量中微子质量顺序的最佳点。此外，该实验还将精确测量中微子震荡参数，开展太阳、超新星等天体物理研究。2013年，江门中微子实验正式立项。2014年，国际合作组正式成立，17个国家和地区、75个研究机构的700多位科研人员，共同投身到这一超大规模、超高精度的液体闪烁体中微子实验建设中。从2015年开工建设至今，10年间，为了在地下建好这个复杂精微的大科学装置，科学家们在这里经历了一系列看似不可能完成的极限挑战。700米厚的岩石很大程度上屏蔽了宇宙线干扰，但也给基建施工带来了巨大挑战。超预期的高压涌水极大地制约了施工进度。地下实验大厅起拱跨度49.5米，高71米，是国际罕见的覆水深埋大跨度超高地下洞室。中国基建工程师们迎难而上，系统解决了这些难题，实现了新的技术跨越。针对中微子质量顺序这一科学目标，项目组提出了2层嵌套式中微子探测器的创新设计方案，内有有机玻璃球承载2万吨液体闪烁体，外以4万吨超纯水代替白油屏蔽放射性本顶，以不锈钢网架结构代替球鞘作为主支撑，满足实验和安装要求，并获得高性价比。4万多支光电倍增管则密排于不锈钢网架上，实现高达78%的光学覆盖率。建成后，实测光产额、能量分辨率远超过此前国际最好水平。不锈钢球形网架结构，中微子探测器的外骨架，是目前国内最大的不锈钢主结构，由800多吨特制低本底不锈钢材料预制成型，并采用不锈钢表面粗化等创新工艺，通过12万套高强不锈钢环槽铆钉拼接而成，实现了无焊接、高精度、高洁净度的地下安装目标。在设计与预研过程中，产出了多项技术发明专利和行业标准。有机玻璃球，中微子探测器的核心舱，是世界最大的单体有机玻璃球，由260多块大尺寸有机玻璃球面板，通过本体聚合的方式拼接而成。自主研发的大型可变镜组合式升降平台，采用液压同步控制，实现高精度顶升，满足了有机玻璃球自上而下逐层安装的要求。项目组和企业通力合作，在高温成型、本体聚合等方面实现了一系列创新工艺和技术突破，达到了高精度、高透光率和极低放射性本底的目标。这些成果在国际上前所未有，推动了行业标准的制定。 项目团队在质量和进度的双重压力下，克服前所未有的难度和挑战，攻克了制造过程中出现的各种问题。在球体建造完成后，大胆设计和启用了内表面检查工装，为探测器长期稳定运行排除隐患。光电倍增管，中微子探测器的眼睛，高能所发明的基于微通道板的新型光电倍增管，并联合国内科研院所和企业完成了研制和批量生产，获得了高量子效率双减阴极和超高收集效率，发明了转移阴极综合制管技术，研制成功超低本底无钾玻璃，综合性能优于国际同款产品，获得多国专利，并应用于其他大科学装置。光电倍增管防水防爆系统，中微子探测器的护目镜，经过大量模拟计算和试验验证，本项目采用的水下防爆系统，可以有效减缓高压水填充真空区域的速度，从而显著降低冲击波的强度，避免链式反应的产生。防水封装采用低透水、高柔性、高强度等多重密封胶相结合的技术，其防水性能国际领先，失效率小于0.5%。为了达到极致的光学覆盖率，相邻光电倍增管之间的最少间隙只有3毫米，给不锈钢结构的精度、刚度和现场安装带来了极大的挑战。项目组针对不同区域制定了相应的安装措施，采取模块化安装方式，高质量完成了现场安装。读出电子学系统，中微子探测器的视神经。项目组自主研发的前端放大芯片及高速采样芯片，完成了国际上第一个大规模水下光电倍增管电子学系统。水下电子学盒及电缆波纹管安全可靠，失效率小于0.5%，达到国际最好水平，实现了4万多路电子学稳定运行。液体闪烁体，中微子探测器的显影剂。项目组与企业合作，生产出国际最高纯度的液体闪烁体原料，研制了一套高洁净度、高气密性、高纯化效率的液闪纯化灌装系统，成功生产了2万吨极低放射性本底、高衰减长度的液体闪烁体，完成了世界上最大体积的液闪探测器灌注。实测有土放射性本底小于10⁻16次方克每克，液体闪烁体衰减长度大于20米。刻度系统，中微子探测器的标尺。项目团队自主研发了多维度高精度的能量、位置和时间刻度系统，为中微子探测提供了统一基准。在大体积探测器中实现了厘米级全自动刻度。反复合探测器，中微子探测器的防护服。项目组研发了大流量超低本底纯水制备系统和国际首创的微气泡脱气膜组合除冬装置。
我们现在开始正式灌注，启动。
成功生产出高透明度异动超纯水。在平地周围岩石放射性本底的同时，它和顶部竞技探测器联合，高效甄别宇宙线造成的干扰信号，为高精度探测中微子保驾护航。控制放射性本底工作，贯穿了探测器设计、原材料选取及加工制造、安装全过程。通过选择特殊的有机玻璃、打磨抛光清洁工艺以及表面防护、最终清洗、液闪纯化和灌装设备密封等一系列严格的措施，最终达到了低本底的目标。此外，为进一步提高江门中微子实验确定中微子质量顺序的灵敏度，项目组在台山核电站内，距离核反应堆仅44米的厂房内建设了台山中微子实验，为江门中微子实验提供精确的反应堆中微子能谱，并开展反应堆中微子能谱反常的研究。江门中微子实验的建设是一段充满非凡挑战的历程。经过国际合作组700人、合作企业上千人10几年的坚持和不懈努力，攻克并解决了一系列关键核心技术和工程难题，于2025年8月成功完成建设，开始正式运行。
现在启动物理曲速，
达到了前所未有的技术指标，有望率先解开中微子质量顺序之谜，实现重大科学突破。
Just now, we have seen the journey of JUNO. Today, actually, we are here for two things. First, we are here to celebrate the completion of JUNO, and also we are here to release its first physics results. Now, let's invite researcher Wen Liangjian, physics analysis coordinator for JUNO, and the deputy director of IHEP, to present the first physics results of JUNO.
Okay, dear distinguished guests, dear friends, it's my great honor to be here to report the first results from our JUNO experiment. So you already see this plot. It's the when we finished the liquid cylinder filling in August 22, and then we take the actually 6 months time since the water filling to the scintillator filling. Use this time to understanding our detector, to study the detector performance, and in the end, we successfully to use a short period to produce the good results in a very quick time. So here, first show you the golden event in the anti-neutrino reactor, anti-neutrino events in our detector. So the left plot is the positron signal, and the colorful points show you how many photon electrons collected by each photon multiplier. You see it in this video. And on the right plot is the delayed neutrino signal. And they coincidence in time and space, which identify anti-neutrino signal from the reactors. So our detector has been stably running from the first day of the data taking. Our data taking efficiency is very high, higher than 97.8%. And we used the beginning of the data period to do the calibration, to understand our detector and to study the background. And then all the rest is the good data for the physics data. So in the end, we used 59.1 days as our data set, which I'm going to report in the following. So first, I will show you the initial performance of our detector. And actually, the paper was posted on arXiv. Unfortunately, number is not ready yet, but you will see it in hour if you check the newest page. And then the paper is submitted to Chinese Physics C. So first, you already see the video just now. And to achieve a precision measurement of the neutrino oscillation parameters, there are a few key factors. So here I would like to highlight a few of them. So first, we need a very high efficient water Cherenkov detector to tag the cosmic muons and to reject the cosmogenic background. And then the inside of the liquid cylinder should be very clean to make sure we have a low background for the reactor neutrino measurement. And also the whole detector equipped with more than 20,000 PMTs, which will achieve unprecedented energy precision, including the energy scale uncertainty and also the high energy resolution to be able to match the precise oscillation. So for the VITO detector, the key point is that we need to make a high transparency water. So we use the ultra pure water to fill the whole water pool. And in the end, we keep improving the resistivity of the water and also the transparency of the water. So we achieve the 75 meters attenuation length in our water pool. And this results in a very high efficiency to tag the cosmic rays, very close to 100%. And this will guarantee to reject most of the background caused by the cosmic muons. And with this detector, we are able to measure the flux of these muons and also the angular distribution in azimuth angle and phi angle, which is in the horizontal plane. So look at the data and the Monte Carlo. They agree quite well, which means we understand first our detector, and we also understand the mountain profile near this region, a few hundred kilometers mountain profile, and also the density properties of these rocks, so which can produce this nice agreement between the measurement and the prediction. So for the inside of the detector, we have a 20 kiloton liquid cylinder, and we should make it to be very clean. So how clean is it? Imagine that this 20 kiloton, you will have like a dust inside those, this whole volume to be less than or on order of tenths of a milligram in this whole volume. So this is a very challenging task, but we managed to achieve it, as you see in the previous video. So all these critical specifications of the detector, like the single event rate inside the volume, and also the uranium and the thorium radioactivity, and also the radon are all under control. So take an example of this radon. So radon is not good for healthy, but also a big enemy for our experiment. So this value, this 1 millibecquerel per cubic meter is roughly like 500 atoms per cubic meter. So this is a very, very small number, and we managed to achieve this. And for the scintillator, we also need a high transparency. And you see the how we control the quality in the video. And in the end, we managed to have very good attenuation length, better than 20 meters, and also very low level of the background in radon and in the other isotope. And this shows you the history, how we working hard to reduce the radon level in our detector. So for the analysis, during the commissioning from the water fitting up to the scintillator fitting, we spend a lot of energy on understanding the low level features. We call it the foundation of the analysis to understand our detector. I'm not going to go through all these numbers, just to shock you that to understand the precision of the detector, we did a very extensive study from the PMT and the electronics, etc., and end up with high precision of the energy measurement. So as you also heard in the video, that we deploy a calibration system, very comprehensive calibration system, including 1D, 2D, 3D calibration using the one-dimensional calibration along z-axis and the two-dimension calibration along a plane. And also in the future, we will deploy a 3D calibration using a remote controlled, automated remote vehicle in small vehicle in the scintillator to calibrate. And all these calibration sources show you a nice data. As you can see, all these calibration peaks using man-made calibration sources. And with this calibration data, we are able to reconstruct our energy to a sub-% precision. So this is an amazing measurement. We never thought about with such large detector with a very short time and a very good measurement, we can achieve sub-% precision in the very beginning. So as you can see, this plot show you the calibration points we used in this data. So the central one and the two-dimensional one, and also the uniformly distributed events in a detector. So this plot show you how precisely we measure and reconstruct our neutron energy peaks, and also all sorts of different calibration sources. And in the end, the precision is about 0.5%. And we also achieved a high light yield. You already heard in the video that to produce a high light yield, we need a good transparency and a good recipe for the liquid scintillator. And this value now we obtained is much better than what we designed. And the whole detector is quite uniformly responsed across the whole detector, and the uniformity is within 1% in a central region that we used for this analysis. And the energy response is a key factor for our oscillation measurement. And again, due to this great detector, we managed to have also 1%, less than 1% uncertainty, or you can call it error in our energy measurement. So we have two PMT systems. One is the small PMT, another is large PMT, and the measurement of these two systems are consistent, highly consistent, and also have a very good agreement with our Monte Carlo within a percent level. And this is never achieved in my previous career about neutrino experiment. So I'm so excited that this detector can achieve this in a very short time. And for energy resolution, it's a challenge task for our future target of the neutrino mass ordering measurement. For now, we use the alpha sources in the detector. We reached better than 3%. With the germanium calibration source, we achieved 3.4%. And we know there are some space we can improve, and this will be the major target for the next half or a few years. So I show you that the current detector performance meet our requirement, or some of them are much better than what we designed. So based on this great detector, we are able to use a very short period of time to produce very nice results. So I report what we achieve. So again, the measurement of these results has been posted into archive. You will see it in our, and we will also submit it to journal soon. So first, the principle. You heard from Yifang's talk that the JUNO will measure the reactor antineutrinos from the two major power plants, the Taishan and Yangjiang, and they are at equal baseline, which means they have an equal distance from the reactor to here. So be able to measure these small oscillations. You can see these small oscillations. And this cartoon nicely shows you the scale, the size of the points, the circular dots or plates, show you the scale of the detector. So I was working on diabase, so it's relatively small compared to JUNO. And this is JUNO detector, and this is another experiment in Japan. So with this big detector at the optimal location, we should be able to measure precisely the oscillation parameters and the future mass ordering. So this shows you how we select the neutrino signals. So basically, you're looking for very rare events from tons of background events. So this shows you the characteristics of this antineutrino signal. They are coincidence in energy, time. So this A is energy, B is time, and C is the space. So you see these distributions are all agree with our expectation, and these 2D plots actually show you how clean is our signal. All the antineutrino signals in this red dashed box, and all the others either background and or very clean region in the other area, which show you the clean signal in this box. So as I already mentioned, the precise measurement and calibration of our detector will guarantee the very small uncertainties, and this will lead to the high precision measurement of our oscillation parameters. So I won't go to details of the analysis, but show you we did a careful evaluation of the signal, the efficiency, and the backgrounds, and observed the reactor neutrino signal as a function of time, and these data points agree with the prediction quite well weekly. So based on this data set, we do the oscillation measurement. And there were 3 independent analysis teams in our collaboration, which provided the fast and robust analysis, which lead the current results. So this is probably the most exciting plots. Show you the black dashed line, show you the long oscillated spectrum if the neutrino does not have oscillation. And this is what we measure in the data points. And with a very small fraction of background, and in the shaded region is the predicted reactor neutrino. So this deficit, large deficit, you can see is clearly oscillation signature, and this will lead us a very precise measurement of the oscillation parameters. And we developed a comprehensive statistical analysis tool. I want to introduce you in detail. And we measured the neutrino oscillation parameters in this red box. For the oscillation amplitude, sine square theta 1, 2, we achieved 2.8% precision. And for the oscillation frequency, namely the delta m square, the mass difference of the neutrino mass, which achieved 1.6%. And this plot shows you the comparison with the other experiment. This is our confidence confidence levels of our measurement. And this is the star is the best fit and with the error bars. And we compare other experiments, which show you how good we are. And the significance is that this measurement, compared to the past 50 years solar experiment, were better than all of them, and even better than the combination of the solar experiment, as you can see in this line, the all solar points. And even compared to the other direct measurements, our precision is improved by a factor of 1.6. And this precision measurement is just the start. In a few years, we will improve the precision to be much better than 1%. And this will largely improve the understanding of the unitarity of the neutrino mixing and open a gate not open a gate, but allow to us to better understand or probe the new physics beyond the standard model. So this is a short summary. It's essentially the same as Yifan's talk. So I want to emphasize that with this huge effort from all the collaborators and the supporters and the great detector, we achieved to release the results today. Let me back to this plot. Thank you.
Thank you. So after 12 years, now we have the first business result. This is an exciting accomplishment. The successful experiment has already achieved some physical results thanks to the support from the government and organizations. Now we would like to welcome some of the representatives from some international partners to deliver a talk. Now, next we would like to invite Deputy Head of Mission of the Italian Embassy, Minister Cristina Carranza. Over to you.
Distinguished representative of government, research, and academic institution, esteemed Vice President Ding Qibiao, and Professor Wang Yifan, distinguished guests. It's a great honor to be here today and to join this day of celebration. Last week, the Italian Minister of University and Research was in Beijing and had fruitful meetings with both the Chinese Minister of Science and Technology and the Minister of Education. On the same days, Beijing hosted the first forum of presidents of Chinese and Italian universities and the 14th edition of the Innovation Week that took place this year under the theme of Boosting Innovation, Building a Sustainable Future Together. The Innovation Week that took place both in Beijing and Hangzhou was attended by a wide academic, scientific, and research business community from Italy and China, and confirmed the commitment for a mutually beneficial collaboration in areas of common interest. We are here in Guangdong Province, which has recently donated to its people the scientific and architectural marvel of the Science and Technology Museum of Shenzhen. In the museum, you can see an original copy of the dialogue concerning the two chief world systems by Galileo Galilei, an ancient book from the 17th century surrounded by wonders of modern science and so sprinkling the two extremes of an uninterrupted timeline. Italy is a country evolved through science and art, culture and innovation, and we are delighted to see how the ancient Chinese culture recognizes and values our legacy. We have gathered here to celebrate the success of an international collaboration composed of brave scientists and have been pursuing remarkable achievement for 10 years. Achievement that could shed light on the fundamental constituents of our universe and probe our comprehension of its evolution. It is just the beginning of JUNO, but it would be hard to imagine a better start, as we witness today. Neutrino physics belongs to the legacy of Italian scientists. Edoardo Amaldi and Enrico Fermi named neutrino particles as a joke, following the intuition of Wolfgang Pauli. Solar nutrition have been investigated for decades at the Gran Sasso Underground Laboratory, a scientific and technological marvel of Italy. At Gran Sasso, the Borexino collaboration developed new techniques to achieve an unprecedented purity of scintillating liquid used to detect neutrinos. Such technique and the related machinery have been one of the most relevant contributions by Italian scientists and research institutions in the process of escalating from Borexino to JUNO, conceptually and in kind. The readout electronics of the detector profit both from the contribution of Italian industries and its distributed computing from Italian institutions as well. We are proud of being partnered in this endeavor, and we are looking forward to its future achievement, conscious that fundamental research is a crucial investment in our future, casting at the same time bridge among culture and people. We are fully aware of the relevance of the extension of the scientific and technological collaboration among the Institute of High Energy Physics of Beijing, that was also visited by our minister, and the Italian Institute of Nuclear Research. And besides the research and development of new technique, the impressive relevance of the joint scientific production for science and significance, and the importance of the contribution for the comprehension of our universe. We value the construction of a safe harbor, where joint management leads to unprecedented achievement, and the joint training of our young researchers and technicians build the scientific community of tomorrow. Let me thank you again for this invitation today, and I wish you great success for the future and years to come. Thank you. 谢谢。
Now we would like to welcome the speaker from Germany, He Hong, from the German Health Association. Over to you. G leaders and scientists and President Ding and Academician Wang, on behalf of German Health Association headquarters and other international scientific organizations and science funding agencies participated in the JUNO project, I would like to extend our heartfelt thanks, gratitude for the invitation to attend today's inauguration ceremony. China made tremendous investment in this project, about 2.7 billion RMB in this monumental advanced scientific infrastructure. Despite severe disruptions due to COVID-19 pandemic, JUNO could be completed successfully within the scheduled time at China's speed, within budget. My highest regard to this project. It is anticipated that this project will become the world's most advanced neutrino research platform, will achieve remarkable breakthroughs in scientific experiments and international collaboration over the next 30 years. The Helmholtz Association, which I represent and work for, comprises 18 German national research centers and laboratories. It is dedicated to strategic applied basic research using large-scale scientific facilities. Consequently, our association maintains a strategic partnership at the institutional level with the Chinese Academy of Sciences, the Institute of High Energy Physics of the Chinese Academy of Sciences, which proposed, designed, and constructed the JUNO project, stands as China's strongest and most distinguished institution in high energy and particle physics. So in 1978, before the signing of the Sino-German Intergovernmental Agreement on Scientific and Technological Cooperation in 1917, a delegation led by the President and Vice President of Max Planck Society visited China in 1974 and signed a formal cooperation agreement with the Chinese Academy of Sciences. Although the Helmholtz Association was not established at that time, its member institutions such as DESY in Hamburg and GSI in Darmstadt had already formed strategic partnerships with the Institute of High Energy Physics and the Institute of Modern Physics of CAS in 1975 and 76. In January 1978, the first researcher group of 10 researchers from CAS and the University of Science and Technology of China went to DESY to work with our team conducting particle physics. Professor He Shengchen, former director of IHEP and the first doctoral student of Professor Samuel C.C. team, after China opened its door, worked at the DESY for 8 years. He returned to China in 1985 and became the first and only Chinese postdoctoral researcher under the newly established postdoctoral system that year. Also noteworthy is the CAS academician Professor Wang Dazhong, former president of the Tsinghua University and recipient of the National Major Scientific and Technological Progress Award in recent years. He was supervised for the doctoral research in FEJ and could have finished his thesis in 21 months in 1982. So Professor Wang is the first Chinese doctoral graduate trained by a Helmholtz Center. The number of the Chinese researchers and PhD students has been increasing even during the 3-year of COVID pandemic. The total Chinese individuals stands at about 1,900. So every year, there are about 1,900 Chinese individuals coming here. Many of them could have been playing vital roles as key personnel in numerous international positions. China's scientific and technological progress has grown exponentially, especially after China's opening up to the outside world. Every year, China enrolls over 100,000 doctoral students, 2/3 of them in STEM disciplines, and China recruits more than 35,000 postdoctoral researchers. Not only the research funding, but also the quantitative scientific indicators across numerous disciplines. China has already approached or even surpassed the United States. Just 1 month ago, on October the 16th, the National Natural Science Foundation of China and the German Research Foundation celebrated the 25th anniversary of their joint office. Since 1988, and particularly after the center's formal establishment in 2000, bilateral exchanges and cooperation in fundamental scientific research between China and Germany have evolved from initial contact to comprehensive academic partnerships. So we are going to strengthen the partnership in foundational research. In particular, we would like to introduce the excellent scientists from Europe to China to conduct studies. Influenced by the pandemic and the Russia-Ukraine war, the international political landscape and economic conditions have undergone dramatic shifts since 2019, especially since 2022, after the U.S. Trump administration takes office in 2025. And there's also the geopolitical conflicts, and also about the whole Moscow office was shut down 2 years ago after the war began. Our Israeli office can no longer operate locally due to the rocket threat from Gaza, and they came back to Berlin. Several prominent German scientists that I know, they told me that they currently avoid visiting China because they may run into experts from Russia. They don't want to fly Chinese airlines since they still have to go past Russian airspace. There are some unknown factors influencing us. Science has no borders, but scientists have their own homelands. Every individual and team holds their certain position and opinions and bias. However, the humankind is now facing challenges. We only have one planet. So we are well-trained scientists. We are equipped with better information, sound logic, and analytic skills. We shall help our fellow citizens. And we would like to have more equal exchanges and promote mutual understanding between people and cultures. As scientists, we can harness the light of science and technology to build mutual trust among different races and nations, advocate for civilization and development, and oppose hatred and violence. This is the responsibility of the scientific communities. I got my doctoral degrees in Germany, and also after I returned to China, I worked in Beijing. My colleagues were people who work in the aviation. Mr. Yang Liwei was my colleague at that time. So the human activities in the aviation, in the space sector, so that humans are indeed great. But however, humans can also be very small compared to the vast universe. So the Earth is just a small part of the universe. So the Earth can be as small as dust. About 10 days ago, I was in Berlin. There was a Falling Walls Science Summit in Berlin. It was initiated in 2009. It is a scientific summit which recognized the breakthroughs in this research. Now this year, we have teams from Tsinghua University that have won the award. Mortimer Moss at the time, when we interviewed her, he said something like this: not just I am the astronaut, so everyone can be an astronaut, because we are all living on Earth. We are all floating in the universe. Of course, in China, we say that there is the harmony between humans and the universe. We have been thinking about the meaning of life and the source of universe. JUNO project was started in 2008, and it was set up as a project in 2013 and started development in 2015. 10 years have gone by. The project had received support from the Neutrino research team, and also we have a committee in Germany that provides support to find universities to join this program. Today, we have representatives and teams from GSI, and also scientists from Czech, Slovakia. Professor Ludova and his postdoctoral students are also joining us today. Indeed, I would like to thank Chinese government and the Guangdong Provincial government and Chinese Academy of Sciences for their investment in the infrastructure. And this is actually a contribution to the high energy physics and the development of cosmology. I would like to thank the scientific organization. Indeed, very grateful. I would also like to thank the construction team. Like Mr. Wang mentioned, they actually work around the clock to complete this project. We sincerely we hope that on this platform we will make greater accomplishments. We hope that we will be able to deepen international collaboration as well. Thank you.
Now let's give the floor to Mr. Fermin Kuvas, Director of the CNRS office in Beijing.
Dear representatives of government, research, and academic institutions, dear colleagues of the Chinese Academy of Science, dear scientists from China, from Europe, and overseas, dear guests, Hao. The French National Center for Scientific Research, the CNRS, is honored to be taking part today in the celebration ceremony for the Jiangmen Underground Neutrino Observatory, JUNO, in which the CNRS has collaborated for more than 10 years. Our institution is a multidisciplinary public research organization that covers all scientific disciplines, from chemistry to biology, from social science to particle physics. We collaborate intensively with our Chinese partners in all these fields, whether they are research organizations or universities, and in particular with the Chinese Academy of Science, with whom we have a long-standing agreement since 1978. The CNRS is the second largest academic public research organization in the world, just after the Chinese Academy of Science, as we like to say. And since the Institute of High Energy Physics of the CAS leads this JUNO experiment, it was straightforward to us to join to the outset of this fascinating adventure. JUNO is a remarkable and unique neutrino research experiment designed to measure solar neutrino oscillation parameters with unparalleled precision, as we have seen and confirmed by the first results that we have seen this morning. JUNO paves the way for determining the mass hierarchy of the three known neutrinos and measuring 3, or maybe 3.5, if I understand well from Professor Wang Ifan talk, the 3 of the 5 parameters that describe their oscillations. The JUNO experiment is one of the most significant research projects tackled by the Franco-Chinese Particle Physics Network, which has been established in 2007. This dynamic and successful network has brought together a community of around 400 physicists and engineers from 17 joint CNRS university research units in France, as well as 5 institutes of the Chinese Academy of Science and 23 universities in China. This network has fostered a strong collaboration between China and France in the field of neutrino physics, involving permanent staff as well as student exchanges. The CNRS is proud to have played a significant role alongside with 74 institutions and over 700 scientists that contributed to the project. We've contributed in the design and the construction, and in particular with 2 significant major contributions of CNRS at this stage, which are the development of the top tracker of the detector, as well as in the photomultiplier system of the central detector. The CNRS constructed the top tracker, including supply of 1,200 electronic cards, to detect and characterize cosmic background so that they are not confused with neutrino signals. As the photomultiplier system, the CNRS provided electronic cards and the firmware of electronics that are key components to reduce systematic uncertainties associated with energy measurement, improve muon reconstruction, and optimize supernova neutrino detection. The launch of JUNO is the result of significant joint research and development efforts in neutrino particle detectors and engineering. JUNO opens new avenues for frontier measurements in neutrino physics and cosmology, in which the CNRS is ready to further collaborate closely with Chinese and international partners. I am proud to share with you that to reinforce the collaboration on the results of JUNO experiments, a new joint laboratory based at the Institute of High Energy Physics in Beijing, entitled France-China Particle Physics Laboratory, ruled by the CNRS and the Chinese Academy of Science, is at the starting blocks for being operational in 2026. This lab and the CNRS office in Beijing, which I represent, will encourage more French researchers and to travel to China to assist with the operation at the upgrading of JUNO, if this is needed, and to maximize the value of the recorded data. This will enable us to achieve the world's best measurements of neutrino properties and prepare us for any neutrino astronomy event in the megaelectron volt range that could occur during the detector's operation. Overall, the CNRS congratulates on the successful construction of JUNO and confirms its commitment to continue in fruitful collaboration with the international community around this unique facility in neutrino physics. Thank you all, and good success for the future. Thank you.
下面我们有请俄罗斯联合核子研究所。
Now let's give the floor to Mr. Eugene Yakshev, Director of the Dazanapov Lab of Nuclear Programs, GINR, please.
Okay, dear ladies and gentlemen, dear colleagues, dear friends, it's my pleasure to be here today to celebrate JUNO inauguration and first results. Thank you for inviting me. I am sure that here and right now one of the most important and most significant events in the modern physics is taking place. Today, we come here to inaugurate a ceremony of the JUNO experiment, an experiment that will for sure shape our understanding of physics in the coming decades, and perhaps, I hope, become the first experiments in new physics beyond the standard model. First of all, on behalf of Directorate of Joint Institute for Nuclear Research in Lubna, as well, of course, on my own behalf, I would like to congratulate all of you on this huge achievement, the successful launch and the first result of the JUNO experiment. And we know it was preceded by a lot of work of hundreds of people. Today, we see how these incredible efforts of incredibly talented people have led to another remarkable milestone, the acquisition of first data and even to the first results. Thus, the most important time is to come, the time to dive deeper into fundamental knowledge and to unlock secrets of the universe. This is because neutrino physics is a field of science that helps to understand how the universe works and to reveal its most incredible properties. The start of JUNO data taking was anticipated by everyone, and JUNO undoubtedly has the potential to become one of the most impressive modern experiments. We at the Joint Institute for Nuclear Research are proud to be part of JUNO, and there are two reasons for that. The first one is that we are proceed with mutual productive cooperation started within the Diabay experiment, which led to one of the most fundamental results in this century. And the second reason is that we uphold our own glorious traditions, since Bruno Pontecorvo, who proposed the very idea of the way to detect neutrinos, inverse beta processes, worked in Dubna for many decades. Almost 70 years are passed till first neutrino discovery. And today, thanks to JUNO, neutrino physics grows in more and more precise field of science, with accuracy of measurements and the level of percentages. It is these levels of accuracy where the most captivating effects are expected. Experimental data are already being taken, and we even see some results, and we all, first and foremost, the scientists who constructed the experiment, and of course the physicists everywhere around the globe are eagerly waiting for breakthrough results of JUNO. So I brought from Dubna a small souvenir for collaboration. I will show you. It's like this, and it has two inscriptions. One is say, waiting for breakthrough results. And I am convinced JUNO will achieve them. Actually, here is a bit more written. The second sentence is, science is actually slogan of our institute, JNR, science brings nations together. And this is about our strength, our international collaboration. I am sure that collaborating internationally, we will achieve all the results originally planned, or maybe even more. We will be lucky and will get completely unexpected results, which now even cannot be predicted. I really hope on this. On the part of JNR, I promise that we will continue making every effort to implement all of our most ambitious plans. I hope our JNR scientists will contribute to this implementation a lot. Noting that we are international collaboration, I would like to emphasize the leading role of China in the experiment. Chinese institutions have laid the foundation of JUNO. The experiment became possible only thanks to your scientific courage and also, of course, to your administrative and financial support. I would like to thank my Chinese colleagues for providing us with opportunity to be involved in the experiment, for your attentive attitude to our employees, and for creating comfortable working conditions for them. We believe that JUNO will really advance science in China and around the world. Once again, I congratulate all of you on official launch of experiment on the first data, and wish JUNO a smooth and troubleless operation. So let me end my address by wishing JUNO new outstanding result. Thank you.
Next, we are going to start the Q&A session. 4 members of the JUNO collaboration will give detailed explanation of the physics results. Wang Yifang and also Giacomo Ranucci, physics analysis leader Wang Liangjian, and myself will be answering the Q&A session. Hello. Hello, I'm the journalist from the China News Agency. So we did some content about the positive high accuracy that confirms the basis of solar neutrons, which suggests they might be some. We know that there's a lot of attention in the new physics, but how long is the confirmation going to take? I would like to ask how long it's going to take for the confirmation. Thank you for your question. So we saw some data about the previous experiments. We are looking at the oscillation parameters of the solar neutrinos. The two experiments have some differences, not very big or not very small. In the future, we are going to improve the precision, and also international experiments may also improve their precision as well. So when can you get results from the solar neutrino experiment? It's going to take 2 to 3 years for us to have results for the solar neutrino, maybe 2 years. Any more questions? If there are no further questions, we are going to wrap up the Q&A session. Any more questions from the floor? Hello, I'm a journalist reporter from Xinhua News Agency. So the JUNO laboratory, the purpose is to detect the order of the neutrino mass, and that is the primary goal. And I would like to know more about your subsequent research plan, and how long is it going to take for you to achieve your scientific goals for the future? Well, we are going to start working in the coming few years in order to confirm the mass order. We think that it's going to take about 2 years. That is our preliminary plan for the coming years. We feel that it's going to take 2 more years to get some initial results, initial signs. So it's going to take 3 to 4 years to finally confirm. And from the China Scientific Journal, in the future, JUNO will have a double beta laboratory. So these experiments how will you update the existing experiments? How do you go about it? Well, after we finish the neutrino mass hierarchy measurements, and then based on the liquid scintillators of existing detector, we are going to mix in the double beta decay nucleus. The specific number of the nuclei has not been determined yet. Maybe after 2030, 50 to 100 tons of the double beta decay nucleus will be put into the systems, the existing neutrino, to look for the double beta data. So your questions are a little bit scientific and technical. We welcome the panelists on the stage to respond to the questions as well? Hello, I'm a reporter from Xinhua News Agency. So the project group consists of members from different countries and regions. In the future, in terms of international cooperation, what are the plans and how do you pool these resources from different countries to conduct the cutting-edge physics research? Right now, we already have 700 members for our projects from 17 countries and regions and 75 organizations. Our collaboration will be deepened on this foundation. Maybe we are going to have a small number of new international members join us, but there will not be too many new members because we have basically completed the project. If we are going to take on new members, they need to make big contribution to the project. So in terms of the double beta experiment, before that, the opportunity for taking on new members is not very big. But after that, maybe there will be more opportunities for international members because at that time we will need new resources. At that time, new members can join us. 好的。
A very important characteristics of this experiment. We are many groups from all over the world, bringing in expertise, competence, knowledge coming from the liquid scintillator field from all over the world. And I strongly believe that one of the strengths of this experiment has been so many different experiences joined together to achieve such a great result. So definitely the international collaboration will continue, will be strengthened. We know that all the funding agencies after this success will be even more motivated to contribute to this experiment. Clearly, we are now entering a different chapter of the life of the experiment, which is the moment of data taking, the moment of analysis. So not so many groups for construction can enter, but the analysis usually attract students, young researchers from all over the world, and definitely will motivate the funding agency to continue to support this experiment. I hope also through the next stage. This is something that clearly will have to be discussed, but we strongly believe that after the successful end of a mass hierarchy determination in few years from now, the second stage of experiment, so the transformation to a double beta decay experiment, will be very attractive for the funding agencies, and I strongly hope that all together will continue this enterprise also for this second part of experiment.
昨天我跟和几个年轻人吃饭的时候聊天，他说这2个月把他们整得够呛。
Yesterday, we have been talking about how hard we have been working over the past 2 months. And also when I asked that, oh, maybe we can do it one more time, and then they were like, no, next generation. I believe that the collaboration program is a very good opportunity for the young people from different countries. It is a good opportunity for growing as well. So at JUNO, the design longevity for this experiment is 30 years. So we hope that we will become good friends for the young generation and lay a solid groundwork for the next generation collaboration. Thank you. Hello, I'm from the Science and Technology Daily. So our experiment has achieved milestone results within 2 months, but the project also underwent a lot of difficulties. What is most difficult about the project? Is it data analysis or the maintenance of the equipment, operations of the equipment? Well, when it comes to difficulties, well, we got good results. That means that our detectors are well made with high precision, high quality data. That is the precondition, premise of everything. We got quick results because we are a strong team. So collaboration in our team was quite strong and inspiring. We got good results. What's difficult is that to achieve precise results, you need to handle all of the errors, and you have to understand all of the factors that affect accuracy, which is really time-consuming and really difficult, most difficult thing to do. So there are 3 groups working on this experiment, and we all got consistent, reliable results. That is why within a short time we managed to release the first physics result. Thank you. 提到
Important to acknowledge the great feat that JUNO has achieved. In 60 days, JUNO has achieved something that our community has not achieved in 50 years. So we have improved in 60 days the previous knowledge of the community in 50 years. And I can speak with great proud for this since I have been working in the field of solar neutrinos, solar parameters, for my entire career. So I started 40 years ago. I saw since the beginning how this field started, how it evolved. It has been an incredible feat, first to understand that there were the oscillation, which was a brand new discovery, then see how one after the other, the mixing parameters were unveiled and how the precision of the knowledge was improved by experiment after experiment. So an incredible, difficult feat, a typical scientific endeavor, which really represents one of the crowning moments of modern science, which is summarized by a knowledge in what we call the particle data group publication, which is the summa of the knowledge of the physics in a certain field. And JUNO in 60 days has practically went along the same path, reached a precision that altogether, all this experiment took 50 years to reach. So this really witnessed to me the power of this experiment, what this experiment can achieve with years of data taking. As somebody already said, really this will be a landmark experiment that will shape the landscape of neutrino physics over the next years by sure. So I had to say that for us, international member of the collaboration is a great success and a great honor to have been in condition to work so effectively with our Chinese friend to reach all together in a very coherent way this great success, which really crown a field of physics, that of the solar parameter, in an unprecedented way. Thank you.
We may stop here, and we have final remark. Okay, so if there's no further questions, we stop here for the Q&A. I know that many of you already had Q&A yesterday, so you exhausted your questions. So, okay, thank you very much.
Thank you.
Thank you.
Okay. So, 最后
So, in the end, let me express thanks. Since the proposal for JUNO, governments and funding agencies at all levels, both from China and elsewhere, have provided long-term support. After more than a decade of joint efforts, our leading neutrino experiment facility has been constructed and officially began operating, becoming a powerful tool for further research. On behalf of IHEP, the initiator and leader of JUNO, I express our gratitude to all the governments and funding agencies. I also extend our thanks to all the leaders, experts, and guests present here today. Finally, I declare that concludes today's event. Thank all of you for your time. Thanks.
各位嘉宾，大家好。然后我说一下会议的事情。我们接下来。
Okay, let me make some announcements from the organizer. Now it's time for lunch. Please follow this lady in pink and this gentleman to the dining area. After lunch, we'll have a tour of our facility. Everybody, please put your earpiece on your seats. Thanks. Once again, everybody, please put your simultaneous interpretation earpiece on your seats.
Yeah, thank you.